Hello, video number 4 in the wave nature of light, electromagnetic radiation and the electromagnetic spectrum. So Charles Clerk Maxwell, 1831 to 79, he explained that light waves are interactions between electric and magnetic fields, and they are actually self-propagating. Before this, no one really knew what light waves were made up of, or what they were composed of, or how they worked. So Maxwell, that was a major breakthrough, and he postulated or found that they travelled at the speed of light in a vacuum, and that's what he looked like. So photography had been invented by that time. So the electromagnetic waves consisted of electric and magnetic fields at right angles to each other. Now, what does that mean? Let's have a look at it. Here's the path that the wave's going through, and the blue is supposed to represent the magnetic field or the magnetic wave, and the yellow is supposed to represent the electric wave. Now they're perpendicular to each other and they're self-propagating is what they're supposed to mean. And so you have a changing electric field that produces a magnetic field, and that magnetic field is changing, which produces an electric field. So it keeps traveling through any medium. That's why it can travel through space or a vacuum, because it doesn't require a medium. It has its own self-propagation. Another way of representing it is, in this case, they've got the electric field going up the axis there and the magnetic field going up the axis there, and so it's varying in such a way, and that's the direction of propagation. And yet another diagram, and so there's the wavelength as well. Now, Heinrich Hertz from 1853 to 94. Now you're going to start notice that around this period and the turn of the century here, from the 1800s to the 1900s, was a big boom in physics understanding. So lots of major breakthroughs, and it was the beginning of the modern physics as we know it. So that's Heinrich, and he in 1887 was able to produce experimental evidence of Maxwell's electromagnetic waves. Before that, it was a theory. It explained lots of things, but there was no evidence for it, and so he was Hertz was able to do that. Showed that energy was being transmitted. How was he able to do that? Well, what he would do is he'd have a high voltage source, and he'd have a loop, and there'd be a gap between here, and that would produce a spark. And then over here he'd have another loop that was identical to this loop, and when a spark was produced over here, or made over here, manufactured over here, it produced a spark over here. And that's because the electromagnetic waves were going from the primary loop, traveling through, in this case, air, but it could be a vacuum, and interacting with the detector loop to produce a current that caused a spark. And that's pretty much the principle that we now use for antennas on radios and TVs and all sorts of things, is basically the transmission of electromagnetic waves. This was his actual apparatus, a bit more complicated than that diagram, but you can see he was generating a spark here from the induction coil and producing a very small spark here, and that was the start of radio transmissions. There was a battle then between him and another guy to send radio signals and various things across the Atlantic and across the English Channel and various places. It started off as Morse code and then got more complicated as they learnt more and more about it. Now, electromagnetic spectrum is when we shine white light into a prism, we saw that we could split it up into different wavelengths, and light is made up of all these wavelengths, visible light, in that spectrum. So we can see that, but this visible spectrum is only part of all these other waves, or electromagnetic waves, which are beyond our ability to see, but we can observe them through the equipment we make. And so we can have, if this is violet, we have ultraviolet, X-rays and gamma rays, and then here we go down to the red, and then we have infrared, radar, FM, TV, shortwave, and this is considered the electromagnetic spectrum of possible waves. This is probably a better diagram. Here we have it's got lots on it. This is the wavelength in meters, so these are shorter wavelengths, these are very long wavelengths. Basically the visible spectrum fits there. There's our ultraviolet, so this is going for more energy. The shorter the wavelength, the greater the energy of the wave, so gamma rays have the most amount of energy, and then as we go to the longer wavelengths we go into lower energy. It doesn't mean that they can't transmit energy, it just means that they don't carry as much energy in each wave. Now if we look at this a little bit more, we can split it up into this area here. We have X-rays, and X-rays can be categorized as either soft, being the lower energy X-rays, or hard X-rays, being the higher energy X-rays. And then we've got some examples of where they fit in. Now this is the frequency, not to be contrasted or compared to the wavelength. They are related to each other using the universal wave equation, V equals lambda F. So down here we have some examples. So in the light we have our sun, then arc welding produces a lot of ultraviolet light. We have X-ray machines, and we have radioactive sources producing gamma rays. Then on the other side we have our heaters, which produce our infrared, our microwaves, our phone towers, TV towers, and various other things. Alright, and so in the next video we're going to be looking at polarization. See ya.